Hey, everyone. Hi, everyone. I'm Eunice Giarta, and I'm co-founder and COO of Monad Labs. And we're here to talk today about scaling a blockchain as a layer one. So to get started, I wanted to go back to the basics a little bit, the fundamental concepts and constraints of a blockchain. So firstly, fundamental concepts of a blockchain. I listed out here like 4 basic things. A blockchain should be decentralized. It should be trustless. It should be immutable. And it should have cryptographic security. These are all pretty basic tenets of a blockchain and parts of why crypto has been such an allure for a lot of people. Amongst these two, immutability and cryptographic security are inherent to a blockchain's design. But decentralization and trustlessness is actually afforded by the implementation of that blockchain. And so these 2 things are actually tested and stressed when you're scaling a blockchain, because when you're having to increase and support a lot of throughput, a lot of transactions, it really does mean that there are constraints in the hardware and software of the implementation. So a couple of specific callouts here are network bandwidth, CPU throughput, state access, and in particular SSD storage, because that's what a lot of non-RAM memory is based off of, and then also state growth. There's a couple of solutions to some of these problems. The first one for network bandwidth would be to raise the bandwidth requirements. And what that means is like asking for a 10 terabyte connection, really, really insanely large bandwidth connections that are oftentimes not available to you as users of a home internet ISP. Like, you just can't get it. So then you're forced to then put all of your nodes that you want to run in either a same geographic locality so that network communications from one node to another are extremely shortened, or so that you can actually get the bandwidth that you need based on said requirements. Similarly, state access could be supported by raising the RAM requirements. But note that RAM and SSD are different, because RAM, well, while it's in memory, it's super fast, but it's also very expensive. The amount of RAM that you would need to emulate an SSD, well, I mean, there's really no comparison. Like the biggest like RAM machines that you would find are like 128 gigs of RAM, and usually you'd have to customize your own box. Whereas with SSDs, you can pretty much find something that's like a 2 terabyte SSD drive. And Apple actually sells some that I think are as big as like 8 terabytes of data as an optional add-on when you're ordering a new laptop. So the scale there is quite massive. So why are these suboptimal solutions though? Well, I think I mentioned some of them just now too, but raising bandwidth requirements, putting everything in the same geography means that you're compromising decentralization. You're basically reducing the distribution, so lower number of participants, increasing centralization as a corollary to compromising decentralization, and also decreasing trustlessness, because now you have to put all of your trust into a smaller number of nodes. Whereas raising RAM requirements, keeping everything in RAM, yes, it's super fast to get the state that you need, but the hardware itself is super expensive. So you price out participants. There are a couple of solutions out there who have chosen the model of using one giant node. Sure, one giant node is great because you would only need to communicate with yourself. I know my thoughts. It's very easy for me to communicate with myself. If I have to communicate to others, of course, there's a little bit of a latency issue there, and a need to be able to more effectively communicate. But then, if me and my thoughts are all there is, then everyone would have to put their trust in me. I mean, I think I'm a relatively trustworthy person, but I'm sure that no one would want to put their entire bank account in my brain. So, one big node, centralized, full trust. In short, like, none of these things are great. Okay, so can we do better? And what should those goals of being better be? Well, firstly, we should try to get the most out of commodity hardware. We should try to preserve decentralization with reasonable RAM and bandwidth requirements, preserve geography distribution with hundreds of nodes, and also raise the limits of what is possible with new software architecture. So here with Monad, we are building a blockchain that is a fully EVM equivalent layer 1, fully redesigned from the ground up. What that basically means is full portability because of the EVM equivalency. So you're able to port over any contract and such, but there's also new software architecture involved there to allow for greater scaling. All right, so the 4 key architectural improvements that Monad introduces is Monad BFT, which is a new consensus mechanism based off of Hot Stuff and DMBFT. It lowers the communication barriers massively. Instead of being quadratic, it is actually linear. We're also introducing asynchronous execution. And so that is basically decoupling consensus and execution. Parallel execution, which many people in this room know, and MonadDB, which is a new custom state database that actually derives its structure from the Merkle-Patricia tree, which is the native data structure for Ethereum. All right, so we're going to focus on just these 2 since I have 4 minutes left, and I'm going to breeze through the rest of these slides here. So asynchronous execution is a new concept for many blockchains. Most blockchains right now are interleaved, and that basically means that execution and consensus need to happen before a block completes. So we'll take Ethereum as an example. Each block is 12 seconds in time. Of those 12 seconds, only 100 milliseconds is actually allotted for execution. What I mean by execution is like running the computation to find what the new state is based on the transactions that are in that block. So if execution is that small, the reality is that consensus takes up most of the block time. Why? Well, because of all of the communication latency. You have distributed nodes throughout the world, and they have to communicate with each other to say, like, do we agree on all of these transactions that are in the block? Do we agree on the final state of all the transactions in the block? So communication is actually the biggest latency when it comes to creating and finalizing a block. So this is just a quick look at what that looks like. So interleaved execution consensus, and each block has both. This across like a chart of time is like, kind of what it looks like. A block cannot start until the next block cannot start until the previous block has finished its entirety. So asynchronous execution is a slightly more optimized version of that, where instead of execution being a part of the block, it is deferred. So we pull the execution piece out of the block, and now the block is only focused on consensus. What that means is that now execution, since it's deferred, will run execution on the ordering of transactions from the first block, while the second one is also now coming to consensus with a new set of transactions, and so on and so forth. And so what this means is that now we can start overlapping a little bit. And so you can see that here. It'll be easier if we kind of stack what that looks like on top of each other here. There's a little bit of a time speed up. So on top, you'll see 5 blocks. It took however much time. On the bottom, we shorten that a little bit. Why? Because again, consensus takes up most of the block time. But this isn't optimized yet. The way that we could optimize that is to actually use the entire block budget for execution as well. And so what we've done here is illustrate that with asynchronous execution, pulling execution out of the hot path of consensus allows us for even more execution time and therefore even more transactions that could be supported and confirmed within each block. All right, so that's asynchronous execution. I'm just going to jump to parallel execution because I have 1 minute and 22 seconds left. All right, so with optimistic parallel execution, right now in Ethereum, everything is linearly ordered and serially executed, one after the other after the other. With Monad, we're still maintaining linear ordering, meaning that transaction 1 that happens before transaction 2 is always going to adhere to those rules. But we can do the work in parallel while still, behind the scenes, while still getting to the same state. How is this possible? Well, optimistic parallel execution, which basically means we're going to assume at the start that all inputs are the same. And we're going to just try to fire off as many executions of transactions as possible at the same time, generate pending transactions, confirm whether those pending transactions are valid, and if needed, we'll just re-execute. Now, I'll run through an example here. So we have transactions 1, 2, 3, 4, and in these examples, let's assume that transactions 1 and 3 are related in a sense that 1 is a dependency for transaction 3, which means 1 must execute before transaction 3. The benefit here is that transactions 2 and 4, being completely unrelated, can be run in parallel without having any adverse effect on state. All right, so let's take a look at what happens with optimistic parallel execution. Excuse me. Okay, so I think what I'm showing here is like, this is the start and this is what we want to get to. How do we get there with optimistic parallel execution? Well, let's just go through the steps here. So before, we're going to assume, I know my time is up. Can I? Thank you. All right, so let's just assume I start with 1,000 USDC, and I am feeling generous, or I've maybe purchased something from Alice and Bob, and I'm going to send them some USDC in transactions 1 and 3. So what we'll do here is that with parallel execution, we're going to assume that all 4 of these transactions are going to be executed at the same time. So the before section are my assumed inputs. With those inputs, the pending results are now that for transaction 1, I am left with 900 USDC, and Alice has 100. And the result of transaction 3 is that I also still have 900 USDC, and Bob has 400. Why? Because again, the assumption that I started with is that I have 1,000 USDC. Now, obviously, this isn't going to work. And so in the pending transaction queue, which is where the outputs are here, I'm going to confirm one by one before committing it to state whether these assumptions are true or not. So we go to transaction 1, it checks out. So we're going to commit that to state. Okay, great. Now our updated state is different. Now I have 900, Alice 100, Bob 300. Transaction 2 is completely unrelated. We can go ahead and commit that to state. Now we get to transaction 3 and we kind of realize, oh, wait a minute. This looks off because I assumed in parallel optimistic execution that I started with 1,000 USDC. With the new committed state, that's obviously not true. Okay, great. So we reject that pending transaction, and we're going to re-execute it. Now we re-execute it. We get to the result we want. Ta-da. All right, so that is optimistic parallel execution in a nutshell. To quickly wrap, this is what blockchain scaling as a layer 1 can look like. It basically means having to rethink the current implementation of blockchains. Like there's various ways in which you can create and add in optimizations into the client itself. So that is what we're doing with Monad. As I mentioned, the 4 optimizations that we're working towards. And in so doing, we are preserving decentralization and trustlessness with minimal disruptions to developers and all participants. That's it, an optimized solution. Ta-da, thank you.